Hi, welcome to this video. So today we'll be talking about the topic application of second order differential equation questions, which we need to find the charge on the capacitor in an RLC series circuit where L equals to 5 over 3H, R equals to 10 ohm, C equals to 1 over 30F, and ET equals to 300V. Assume the initial charge on the capacitor is 0C and the initial current is 9A. What happens to the charge on the capacitor over time? These are the contents that will be included in this video. So first, let's get on to the bio data of each member in this group. So first we have LIAU, which is Jackie, and next Josephine, Mandy, Yan, and me myself, Yin. Let's get on to the introduction. What is differential equation? It is an equation that has derivative whether it's ordinary derivative or partial derivative, which involve a dependent variable and independent variable. For example, as the above, dy dx equals to fx. Next, order of differential equation is determined by the highest derivative appear in the equation. Second order differential equation involves second derivative of the unknown function. It can be written in the form of that. There are two types of equations that can be found, which is homogeneous equation, which fx equals to 0, and a non-homogeneous equation where fx is not equals to 0. And in this project, non-homogeneous equation is used to find the solution to the charge on the capacitor over time.
Next, I will present about the problem description. Our problem is about an RLC series circuit. Values of inductance, resistance, capacitance, and electromotive force, which known as voltage of source, are given, and also the value of initial charge on capacitance and the initial current. We need to find the equation of charge on capacitor and its charge diff over time. First, we have to know what is RLC series circuit. It is an electrical circuit which consists of a resistor, inductor, and capacitor. The three components are connected in series across a sinusoidal alternating supply. Hence, an RLC series circuit is formed. To find the supply voltage across the three components, Kirchhoff's second law is applied. Kirchhoff's second law is also known as Kirchhoff's voltage law. It is a result of charge conservation and the conservation of energy. It states that in any complete loop within a circuit, the sum of all supply voltage, either from cell or generator to provide electrical energy, must be equal to the sum of all voltages across the other components, such as resistor, inductor, and capacitor. The most important is it must be within a same loop. In a simple way, the sum of potential difference of voltage in a closed loop is equal to 0. From there, we can conclude that VR plus VL plus VC is equal to VS.
So right now, here is what we will need to find. We will need to find EL, ER, and EC. And the sum of all of these will be our electric potential in volts. So let's take a look into how we are to find these equations. Firstly, let us refer to Faraday's law and Lenz's law. It is stated that the voltage drop across an inductor is directly proportional to the rate of change of current and proportionality constant L. Hence, we obtain our E of L. Secondly, let us refer to Ohm's law, which is the drop of voltage across a resistor corresponds to the current flowing through the given resistor in the circuit and constant of proportionality R. Hence, we get our E of R. And last but not least, for any given capacitor, the charge Q is directly proportional to the capacitance C and voltage across the capacitor. So when we rearrange the equation, we obtain E of C is Q over C. And since we know that E of T is the sum of E of L, E of R, and E of C, so our E of T will become this equation here. And finally, we must substitute I equals to dq over dt, and we will obtain our final equation. And as observed, it is a second order differential equation. It can be solved by using non-homogeneous differential equation to obtain the general solution in this form.
While doing this project, what we can get from result? First, the general equation of charge on a capacitor. Second, after we substitute the initial charge on capacitor and the initial current, we can get the particular equation of charge on the capacitor. Third, the final charge on the capacitor if the limit of time is exceeded. The objective of this project is aimed to investigate the application of linear non-homogeneous differential equation of second order on RLC series circuit.
Now, let me explain about the methodology. So, as seen in the problem description part, the final equation we obtained is observed to be a second order differential equation. So it can be solved by using non-homogeneous differential equation in this form, where A, B, and C are constants. It can also be expressed in the form of y equals to yc plus yp, where yc is our complementary function and yp is the particular integral. Now, we must solve the question by using non-homogeneous differential equation. So let's take a look into an example, which is this question right here. So firstly, we must find yc, and to do that, we must let dy over dx equals to r, so that we will obtain this equation right here. And after that, we can calculate and obtain the values of r, and as you can see, we have two distinct roots here, so our yc will be in this form. So the second step is to find y of p. So we let y of p is equal to kex, and we differentiate it 2 times because the order of the differential equation is 2. So after differentiating it, we substitute it back into the original equation, and you will get the value of k. So with the k value, you can put it back into the first equation, y of p equals to kex, and substitute the k value and you will get y of p. And lastly, our general solution is simply y of c plus y of p. And we have those 2 values that we got calculated just now. And here is our final answer. And so if we are asked to solve an initial value problem, these are the steps that we should take. So with this example right here, it is given that the conditions are as stated. So firstly, we should differentiate the general solution with respect to x. This whole solution, we differentiate it and we will obtain this solution, this equation. And with the given condition of when x equals to 0, y is equal to 1, we substitute it into the first equation and we obtain a is equal to 10. And we do that for b. And lastly, we have obtained the values of a and b, so we just substitute it into the general solution, and this is your particular solution.
Let's look into another example. Find the solution of the differential equation below. First, we need to find yc. We need to substitute dy over dx by m. By doing the factorize, we can get m equal to 2. Since the roots are real and equal, yc is equal to the a plus bx in the bracket times with e to the power of 2x. Secondly, we need to find yp. That's yp equal to x to the power of r in the bracket ax squared plus bx plus c. Choose r equal to 0. Since there is no terms of yp same with yc, we can use r equal to 0. Then differentiate yp twice, substituting the result of differentiation and the value of yp into differential equation. By comparing both sides, we can get a equal to 1 over 4, b equal to 3 over 4, and c equal to 5 over 8. So yp equal to 1 over 4x squared plus 3 over 4x plus 5 over 8. Lastly, we need to find y equal to yc plus yp. After substituting the value of yc and yp, we can get the general solution of y. Given that when x equal to 0, y equal to 0, and y prime also equal to 0. Substituting x and y into the equation, we can get a equal to negative 5 over 8. Doing the same thing on the equation of y prime, we can get b equal to 1 over 2. Putting value of a and b into the general solution, we can get the particular solution of y.
Result and discussion. Question. The question wants us to find the charge on the capacitor and what happened to the charge on the capacitor over time, and the information of L, R, C, and ET also given. The initial charge of the capacitor and the initial current also given. Step 1. Finding the second order differential equation. According to the Kirchhoff's second law, sum of voltage drop across the inductor, resistor, capacitor will be equal to the supply voltage ET. We use the formula of EL, ER, EC to substitute inside here. Then, we know that this is not our second order differential equation. We use I equals to dq over dt and substitute inside here. Then it will become our second order differential equation. Step 2. Substituting L, R, C, and ET. Step 3. Multiply both sides with 3 over 5 to make the coefficient of first term equals to 1. Non-homogeneous equations are obtained. Step 4. Solving non-homogeneous equation to obtain general solution. First, we find QC. This is the non-homogeneous equation that we obtained, and then we convert this non-homogeneous equation to homogeneous equation to obtain QC. We know that A is equal to 1, B is equal to 6, and C is equal to 18. Then we let R equals to dq over dt. We obtain R squared plus 6R plus 18. Since the equation will obtain complex conjugate root, we use the quadratic formula to solve the equation. Then we substitute the A and B and C inside. We got negative 3 plus minus 3R. Our alpha is negative 3 and our beta is 3. Since our root is complex conjugate, we use this equation. We substitute the alpha and the beta inside. Next, we find our QT. ET is equal to 180, which is a constant. Therefore, QT is equal to C. Then we differentiate it, then it becomes 0. And then we substitute into non-homogeneous equation.
When we substitute into non-homogeneous equation, we got C is equals to 10. QB is equals to C, so QB is equals to 10. General solution. We can obtain general solution by substituting QC and QB inside this equation. So this is our general solution. Step 5. Finding C1 and C2 to get particular solution. Given from the question that initial current is equals to 9 and initial charge is equals to 0, substitute initial charge equals to 0 into general solution to obtain C1. Then Q will become 0 and T will become 0, then we obtain C1 is equals to negative 10. Then we differentiate our general solution because I is equals to dq over dt. Then we substitute initial current equals to 9 and to find C2. When we differentiate this part will become 0. We differentiate this using product rule. When we use product rule to differentiate this, it will become like this. Then we substitute initial current equals to 9. So dq over dt, which is equals to I, is equals to 9. T will become 0. And we obtain 9 is equals to 3 C2 minus 3 C1. We know that C1 is equals to negative 10. So we substitute C1 and we get C2 is equals to negative 7. Substituting C1 equals to negative 10 and C2 equals to negative 7 into general solution to get particular solution. Our general solution is this. Particular solution, we insert C1 and C2 inside. Answer. The charge on the capacitor is our particular solution. By assuming T is equals to infinity, E negative 3T will become 0. The capacitor will eventually approach a steady state charge of 10C over time because this part will be equals to 0. So Qt is equals to 10.
Hello, I'm LIAU, and let's talk about the conclusion of this assignment. The ordinary differential equations can be used to solve engineering problems such as RLC series circuit by applying Kinop's voltage rule, Faraday's law, Lenz's law, and Ohm's law. By applying those rules and laws, a second-order differential equation is formed. The equation is used to determine the angular frequency of oscillation for resistor, inductor, and capacitor of a RLC series circuit. In a nutshell, second-order linear differential equation is used to model many situations in physics and engineering. These methods are equations obtained from the ordinary linear differential equation, are applicable in fields and sectors such as medical field, manufacturing field, energy, technology, and archaeology. Therefore, the application of ordinary linear equation is very useful in our daily lives.